These devinfo structures, one way to walk this device tree is actually to use a library, libdevinfo, and you can also use MDB if I really want to look at the data structures. Are we ready? I think there's a couple USB sticks going around with. Somebody will hand you a USB stick at some point. There's two of them going around right now. Okay, so you can dump out the dev info if you really want to see what's in it, and you probably do want to see, but you probably really don't need to. Let's see, if the device isn't present, if you don't see it in the device tree, then as far as the operating system is concerned, the device physically doesn't exist. So if it's a hardware device and it's not being seen in the device tree, you probably need to look at your hardware, make sure your wires are plugged in right, and even that, you can also try doing things like boot -R if you're on, at least on Spark, and you can sometimes end up seeing the device this way. Okay, there's nothing else new to that page. There's a picture, doesn't add anything. Choose, okay. Nope, I want to move on here because of time. Okay, so how does the system pick which driver to use for a given device? And this is something I see a lot on open Solaris mailing lists. I've got such and such a device and there's no driver for it. What's going on? And usually what people want to say is, oh, let's see your PRT-conf output. And what they do in the PRT-conf output is they look for this property called the compatible property. And generally, these properties, this compatible property, is built using, at least for PCI, it is built using vendor ID, device ID, subclass, and there's a couple other registers that are in the configuration space of every PCI device. And the system actually builds these names up for you based on the information in these registers. So lots of times these numbers here, like the .1 might be a version number at the end of, where's that fabulous thing? At the end of this line here, the .1, for instance, might be a version number. So maybe a new version of the chip comes out and it's .2, and the driver might work just fine for this, but because we don't have a match anywhere for that particular device, the system decides there's no driver for it. So what you want to do typically is when you add the driver, I don't see it here, but when you add the driver, you're going to use -I and specify the compatible property. So here, the skeleton device is driving this particular device. So any device that has this in the compatible property and nothing else has matched it before that, so in other words, this might not be the first field in the compatible property, we'll use a skeleton driver. All right. So a lot of times you don't need a driver. All you need to do is figure out how to use add drive to add an already existing driver that probably is going to work for your device. I mean, if it's a new version number, maybe there's some additional functionality that the driver doesn't have, but you're probably going to be okay depending on what you're trying to do. Question, yes? In order to make the driver work with the new device, we compile the driver to add these compatible numbers to the driver? No. Okay, so the question is, in order to make your existing driver work with the new version of the device, do I need to do anything? And the answer is no, but you will have to rem drive it and then add drive. And when you add drive, you specify -I, and then usually the first compatible property, that whole thing in quotes, and then your driver name. Now, that might work. It depends on what they changed. It's a new version of the device. Maybe they changed something in a non-compatible way, and the existing driver just isn't going to work with it. Okay, but it's worth a try. All right. If the existing driver does work with it reasonably well, then you might think about, well, what's the new features that they've added, and how can I put those into the driver? And that, of course, would require coding. No, the compatible information. It's put in this file etc driver aliases, and etc driver aliases is used to locate a driver for a given device. So the system, when it's coming up, it looks at the device and then it looks for a driver for it. And the way it does that is it goes through these compatible properties and it looks for any driver with the same name. So if there was a driver called PCI 1002, comma 5950 dot blah 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 blah, which is unlikely. You're not going to have a comma in the name. But if it finds a driver with that name, it'll use that driver. If it doesn't find a driver with that name, it'll go and look for a match in driver aliases. If it finds a match in driver aliases, it says, oh, that's the driver I need to use for that device. So if it doesn't find a match on the first compatible property, it tries the next one, it tries the next. If it can't find a match on any, it gives up. It says, well, I don't have a driver for this. When you install a driver using add drive -i. So you would do something like, and I'll just include something up here. You would do something like okay. I don't have something called foo, but it would look something like that, assuming that that PCI 1002.111, etc. was the compatible property for your new was one of the compatible properties for your new device. You want to try to pick a compatible property that's unique across all the devices, but prtconf -vp will show you all of them. Okay? Now, yeah, question. Okay, so skeleton would drive the PCI 10CF, 1301. Skeleton 1 is a different driver for this particular guy. So, which is the one on the top, right? But there may be other devices that have PCI 10CF, 1301 in the compatible list, but they don't have that particular. They don't have PCI 1002 blah 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 in the compatible list. Okay, these may be very similar devices, right? But they're different drivers in this case. Now. Okay, so hardware, registers. So device will have typically a couple different sets of registers. Solaris tends to refer to these as register sets. For PCI, there's a register set 0, which is basically config space. All PCI devices have config space as part of the specification. Device may also have 0 or more I/O spaces and 0 or more memory spaces. And typically, at least one of these register spaces, I/O space normally, is used for doing things like configuring, retrieving status, starting I/O, setting up DMA, etc. And yes, the hardware documentation should describe how to use the registers. My view on writing drivers, by the way, is that the hard part of it is getting the hardware documentation. Okay? So if you have a company you can work with, you got someone in the company who can give you the documentation, and it wasn't written by a Russian who was writing in Hebrew, which was translated by a Spaniard into English, you'll be able to figure these things out. the documentation out. So sometimes the documentation can be not the greatest. Go ahead. Verilog. Yes. You know, I know what it is, but no.
Okay. So I'm just understanding what you mean when you say you can't get the documentation. You can't get the English translation of the Verilog. It's a hard thing to get. I'm not saying it's easy. I'm just wanting to define because the guys who did the hardware wrote it in a language that is perfectly clear to them.
Yes, that's true. And sometimes that means they give you schematics. Schematics and timing diagram, and what you really want is something that gives you kind of the operation. And some companies, I think, are really good with this. I actually think Intel tends to be good doing this. It's my opinion. And AMD as well. They tell you. But the graphics companies, good luck. You want to write a driver for them? Go work for the graphics companies. All right. But basically, the documentation should describe how you use the registers, what the constraints are. If there's timing constraints, it should tell you about it. And if you're fortunate, it's accurate and completely readable. To access the registers, you call this routine called DDI regs map setup. Now, the name can be a little misleading and implies that you're setting up a mapping to the registers. And actually, on Spark, that's exactly what you're doing. But on x86, you may be setting up a mapping. You may be getting port numbers. Depends on the device. Depends on where the registers reside. All right. But this routine, DDI regs map setup, is going to come back, give you a handle, an opaque object that you can then use to access registers on the device. And if you use this correctly, you should be running the same code for Spark, x86, x64. It should be exactly the same source code. All right. Now, once you've got this handle back from regs map setup, you use DDI get and DDI put functions to retrieve and write to the registers. And the way these functions work, basically, if the registers are memory mapped, the DDI get and put functions will access memory locations. And if the registers are in ports, the DDI get and put functions will basically use in and out instructions. Go ahead. Yes, there are M fences or L fences or S fences or mem bars, depending on the hardware, in these functions where needed. Okay. Now, interrupt handling. And we're going to see, I think, a little bit of code for this in just a minute. So interrupt handling, asynchronous events from the hardware. The driver will register interrupt handlers or should register its interrupt handler or handlers with the system using this function DDI interadd handler. The interrupt handler may be called when the device is not interrupting. It may be called when the device is not fully initialized. You should be aware of this and handle it properly. And the handler typically has to tell the system, I got it. Okay. DMA, we're going to get into in a minute. Driver sets up the data transfer between the memory and the device goes and does the transfer. And programmed I/O, basically the driver itself actually does the transfer, typically by reading and writing registers. Another comment?
Well, just wanted to make something. Is there a facility for logging those interrupts? If the interrupt handler is called when the device is not interrupting, that usually qualifies as a log.
There's probably a way to do it with FMA. Okay, but I'm guessing there. FMA is the way, probably is DDI underbar, FM underbar something. The INTRD stuff? I don't know that will do any registering of basically, ghost, of phantom, a device that's interrupting when it doesn't really have any reason to interrupt.
And would you use the same mechanism if you're the interrupt handler and you discover that the device is not fully initialized? You say, hey, whoa, dude, I have to call this error checking code in the interrupt handler, and that goes right in my main tab. I hate that stuff.
I'm thinking about that. I might want a task queue thread if I have a device that I suspect is going to be a little flaky that way, and try to have that kind of handling done by the task queue thread. So the interrupt handler has detected that I'm getting lots of spurious interrupts, and it just kicks the task queue thread and says, hey, take care of this. And then that guy can go and do the error checking and report back to the FMA framework. All right, but I'm guessing at that. Yes. Yes, well, okay. Go down. Okay, so PCI has config space, IO space, memory space. All of these spaces can be accessed by using the DDI regs map setup. There is a special routine for the config space, but it basically is doing DDI regs map setup underneath. And keep going. Okay, so to access the registers, so here's a little example. You set up this device access attribute structure. In here, a version number, endian flag. It's going to be little endian, big endian, don'ts or never swap. So just leave the bytes in whatever order they happen to come in. What you're supposed to do here is specify the endianness of the device, not of the system, not of the bus, the device itself. And then the system will take care of any byte swapping that needs to be done inside of the DDI get and put functions. And I've never seen anyone use anything other than strict order. It basically says multiple accesses of different registers, or the same registers are going to be handled in the order that the reference was made. All right, compiler will not reorganize things, and the hardware shouldn't reorganize things either. You call this DDI regs map setup. You pass in the dev info. So this is typically done in attach. The second argument is which register set. 0 is always, for PCI, 0 is always config space. But other register sets depend on the hardware. The third argument is going to be returned back to you. And this will be some kind of a mapping to the registers. And it turns out it'll either be an address, if the registers are memory mapped, or it'll be a port number. The fourth argument, a 0 here, is the size of the register set. If you specify a 0, the hardware basically says, okay, I'm sorry, the system will basically map in the entire set, whatever that is. And I'm going to come back to this in a minute. The fifth argument is an offset. So this function is used, for instance, to map frame buffers. And you might specify a 0 and a size of 8K, and that might be the first 8K of the frame buffer, which is control information. And then you call DDI regs map setup again, and the second time you call it, this 0 here is 8K, and this is 8 meg because you're basically, the frame buffer is 8 meg large. And the first 8K is control stuff. So you call it twice. This will the first time with a control red pointer, and the second time with a frame buffer data pointer that's filled in for you. This is your device access attribute structure that you passed in, and this you get back. This is a handle. And then to access the registers, you use DDI get and DDI put. You pass in the handle and the register. Here I'm picking up the vendor ID from config space. All right. Now, there is something else I wanted to say about this, but we're moving on, and if I remember, I'll come back to it. Okay, interrupt handling. Yes, go ahead.
Can you think of anything in the PCI structure that prevents that code from being entered? Is there anything in the architecture that prevents PCI from being hot swappable?
You mean actually swapping out a card on the bus? Or
So what other people do is they have the ability to basically down a PCI bus and put in a card
Yeah.
up the bus, and then boom, just that bus gets reconfigured as if it was an initialization, as if it was being booted up.
Where are they doing that? Are they doing it in the driver code, or are they doing that in the BIOS, ACPI?
So I'm just trying to figure out, based upon what you described in that structure, is it possible to add a PCI card to the system? Or to replace the broken PCI card with a new one without bringing the system down?
It should be possible.
Cool, that's what I need.
It should be possible. That doesn't mean I've done it. You think people do it?
So some vendors, when they design their PCI bridge chip, add the features that make that possible. And so it's possible, so part of the extra stuff in the config is you can play with the wires on the PCI bus, tell the cards, I can toggle reset, and I can do a bunch of other things, which make the cards think they're coming back up from a real time. When only these little cards, the rest of the system's up and running fine.
Okay. You should be able to do this, yeah.
Cool.
The attach and detach function have suspend and resume commands. And you can quiesce the device, save state that you need to save, unplug, plug in new. That should all work. Okay, assuming the driver's doing everything correctly, that should work, yeah. All right. Interrupts. Okay, interrupts are assigned priorities. As far as PCI is concerned, the priorities are assigned based on the class code register, so based on the type of device. You can specify different priority. You can have the driver change the priority. You can specify priority in a configuration file. Interrupts above priority level 10 are called high-level interrupts, and you should have special handling for these. Typically what you do with high-level interrupts is you do the minimal amount of work, and then you trigger a software interrupt. The software interrupt runs at a lower interrupt level. Okay, and you can always also trigger what's called a task queue thread, which doesn't run at interrupt level at all. All right, and so a way to specify or retrieve priority, DDI, enter, set pry, and get pry. Interrupts can be fixed, which are basically old-style interrupts, or message signaled interrupts. Interrupt handlers are supposed to return either claimed or unclaimed. So for fixed interrupts, it's possible that your driver gets called even though it's not your device. It could be a different device interrupting. This is particularly true on Spark. Okay, so you tell the device, well, you check the device, and if it's your device, you do what you need to do. You tell the system enter claimed. If it's not your device, you tell the system enter unclaimed, and what the system will do is it'll go and try the next guy. So you've got 4 guys running at the same interrupt level. It'll try the first. No, it's not me. It tries the second. Okay, it's me. Then another interrupt comes in at the same level. It starts with the 3rd guy. So it works round robin, doesn't starve anybody out. All right. So you're supposed to return claimed or unclaimed, depending on whether it's your device. Anything else here? Driver? Yeah, a driver usually needs to tell the device, I got the interrupt. This may depend on the kind of interrupt the device generates. But basically, if there's a way to tell the device you got it, you tell the device you got it so that the hardware stops interrupting. And there's various examples in the source code for this. And in fact, I think we're going to look at a little bit of code here. Most of this code is coming from the BGE driver, Broadcom Gigabit Ethernet. But DMFE has this, E1000G has this, and there are others that have pretty much exactly the same kind of code. So in the attach function, you register your interrupt handlers. You'll see we've got these interhandle table because you may have more than one interrupt from the device. Now, the code here looks to see, does the device do MSI X or MSI interrupts, and if so, it gets the number of interrupts that the device generates. Now, I did this talk, or some variation of this, a couple years ago, and this was largely a group of Sun people. And one of the guys in the audience was a Sun guy, and he said, oh, if anyone has a PCI device that does more than one MSI, let us know, because we haven't been able to test this code. No idea what's going on with it now, but here you get the number of interrupts that's going to be put into count. And the only device I've ever dealt with that had multiple interrupts was a UART on a VAX. For those who don't know what that is, maybe you've, yeah, okay. I thought there might be one guy in here besides me. Okay. So here we set up this H-table array, add the interrupt handler, and we're using the same interrupt handler for all the different sources of interrupt from the device. Usually that, by the way, will be 1. It's called foo enter. And we have 2 arguments that we can pass to our interrupt handler. One is, well, actually, up to you what you want these to be. Typically, first argument is a pointer to state for the instance that's interrupting, and the second argument is an indication of which interrupt it is, if the device has more than one. The UART on the VAX that I mentioned had 2 interrupts, 2 vectors. It gave you one vector if transmission finished, and it gave you a different vector if input was available. But I don't know any devices other than that that do that these days, but the code's there to support it. Okay. You get capabilities. There's various capabilities you can get about the interrupt handling. And one of the capabilities says you can enable all the interrupts at once. This is a block enable. And if you can't enable them all at once, you sit in a loop and enable them one at a time. Now the idea is that once you've done this, you can start getting interrupts. And your foo enter interrupt handler gets called. And the foo interrupt handler, if it's an MSI interrupt, it's only going to be you. You're not going to be called for somebody else. All right? But if it's a fixed interrupt, you may be called, and it may not be your device interrupting. So we check. Is it me? If not, return unclaimed. If it is me, we're going to return claimed, and we go and handle the interrupt. Okay, so somewhere in here, we'll tell the device you got it. You handle I/O completion, handle status changes, report errors, start up the next I/O. You might do all this. You might do it here. You might do it in another thread, a task queue thread. And you can even do a combination. Do some of it here and some of it in the task queue thread, depending on how much time you're spending here. All right. Interrupts are so much fun. Okay, so for DMA, driver has to set up and tear down mappings for the DMA. There's a set of DDI routines to do this. You may need to build a scatter-gather list, depends on your hardware. You may need to synchronize caches. There's a DDI routine that's supposed to do this, although on a lot of machines this routine doesn't do anything. Yes, most of the work is done by these routines, DDI, DMA, XXX, where XXX is, there's about 8 or 10 different functions. Yeah, it mentions there's over 40 routines documented that are DMA related in section 9F. Generally, if you are thinking about virtual versus physical addresses, you are not using the DDI correctly. That's a very general statement. All right. Sometimes you really do want a block of memory that's physically contiguous. And that can be difficult on Solaris after the system's been up for a while. Does everyone understand that? You do. That's all right. I just want to make sure everyone's got that. It can be difficult to get contiguous memory that's physically contiguous, especially after the system's been running for a while. So if you have a device that likes to do 128K transfers and it needs to be, for some reason, they need to be physically contiguous, grab your buffers when you're coming up. There's no good DDI way to do it right now.
That means the 10 gigabit drivers are really hard.
They can be difficult, yes. It's a problem that's currently being worked on. All right.
What platforms are you talking about? Is Solaris or
This is very much all Solaris. I can't speak about other platforms as far as this stuff is concerned.
something about compatible across platforms?
Cross platforms means Spark, x86. If you write your driver correctly, there should be no if-defs for Spark versus x86 versus x64. This is going to be almost impossible. In particular, a couple of the data structures, one of them is a DDI, DMA attribute structure that you may have different versions of. But the code, generally you won't see if-defs.
That's one of the marvelous things about Solaris.
Yeah, it's very clean that way.
What about if you have a device that needs to be virtualized, if you're running hypervisors, what's some?
Okay, I am not aware of specific hooks in your driver for doing that. It doesn't mean they don't exist. I'm just not aware of it. I don't see it when I'm reading code. I certainly don't worry about it for most of the driver code that I work on. So I'm just not aware of it. All right, you're going to have to dig for yourself on that one. The question was, are there hooks for para-virtualization that drivers need to know about? And like I said, not aware of any. All right. Okay, so you have a DMA attribute structure, and here this structure, the documentation for this has gotten a lot better. But some of these things you may not be able to figure out an answer to. Maximum burst sizes. So this is how much data you're going to send in one cycle, in effect, on the bus. So you arbitrate for the bus, you send a burst, and then you let go of the bus, and then you arbitrate, send a burst, let go of the bus. And the value here are basically powers of 2. So this guy can do 2 bytes, 4 bytes, 8 bytes, 16, 32, 64, etc. Bursts. And a problem you might run into with this is that you may not know what the device is capable of. They may or may not have this in the documentation. So then you do what everybody else does. You copy from an existing driver and hope for the best. Generally, this is not going to make your driver not work if it's not correct. It may affect your performance. All right. Yeah, most of these, I'm actually going to punt and say the manual page is reasonably good at describing what these are used for. The scatter-gather list, one entry scatter-gather list. So basically there's no scatter-gather on this device. That's the third to last entry. This guy can do 1 byte transfers. Minimum transfer size is 1 byte. It can basically transfer to anywhere in memory. Low address is 0 and the high address is basically 2 to the 64th. There is a counter register, which looks like a 32-bit register. So you can do probably up to 4 gig at a time.
So ULL means unsigned long.
Yes. All right. And yeah, this flag error, I should mention, if you want to participate in the fault management framework, you will you specify that you will handle DMA errors. All right. Now, I've done much with this. I'd have to look. I'm thinking more by the memory. generally you're going to call some DDI DMA routine, and then so you do the DMA and then you call a routine. And I'm not sure what the routine does, that was the problem. You call a routine, it basically says, was there an error? And if there was an error, then if you're going to support error handling, you report an error. But I'm not sure what the routine is doing. It's checking for the error. I've not looked at it. All right. Now, okay. So, again, I'd like a picture. The way you do the DMA, you set up one of these DMA attribute structures, then you allocate a handle, then you bind an address to the handle, then when you bind an address to the handle, the address is where you're doing the DMA to or from, virtual address. You get back a cookie or set of cookies, and the cookie or set of cookies will have physical address or virtual address depending on the underlying hardware. And you take the addresses from the cookies, you load them into device registers, you tell the device to go. All right? To me, it's a bit more interesting is to figure out, especially on the networking card, do I DMA directly into the packet, or do I DMA into a buffer and then copy the buffer into a streams message and pass it up? And I see drivers doing both. All right? But the idea again is allocate a handle, bind an address to the handle, you get back a set of cookies, you take the addresses in the cookies, you load the device registers, you tell the device, do the transfer. At the end, you basically clean up.
Do you know if there is a command that you can call within Solaris which says copy everything to swap, so that you can force continuous memory?
I have a way to do it, but it's called DD. But no, I understand what you're asking, and no, I'm not aware of one. No.
Because it's a rich set, but it seems to be missing one or two things.
Yeah, that actually shouldn't be that difficult to implement. Yeah, it wouldn't be that difficult. All right. We go on. Okay, so here we are binding the handle to a memory address. The memory address is specified by this &VA. And you can see this routine takes lots of flags. I'm going to basically say, read the manual page. You can actually set up a callback if the routine fails. Here I'm not setting up a callback. If the routine fails, don't wait basically says just return immediately with an error. And reasons this can fail is basically you don't have resources, or you're trying to DMA beyond the limits of the device or the system. And this comes back. When it comes back, okay, so this is allocating memory to do DMA. Then, I think the next page we're going to, okay, down near the bottom here, bind the bind an address to the handle. K-P is basically some kernel address, very likely that you got from the DDI DMA memmalloc. You bind it to the handle. You get back the very bottom here, a DMA cookie and the number of cookies that you got. The DMA cookie will have physical addresses or virtual addresses, depending on whether your system has an Iommu or not. Spark has had Iommus for several years, but x86 and x64 is fairly recent. Iommu basically is a TLB that's in the PCI bridge controller. So what happens is, instead of having to give physical addresses to the device, you give virtual addresses to the device, and the TLB in the bridge actually takes care of translating the virtual to physical for you. Of course, you've got to program the bridge to do this, and the bridge has to have support for it. So here we are going through the cookies and loading a scatter-gather list with the addresses and sizes out of the cookies. And here we're getting the next cookie. So we're basically sitting there going through all the cookies. You can also set up what are called Dma Windows. So if you have a device that can only do 64K at a time and you do a 256K transfer, and the device has a scatter-gather list of 16, you might get 16 cookies in one window. That's the first 64K. You move to the next window. You do the next 16 cookies. You move to the next window, doing the next 16 cookies, etc., until you've finished all your cookies and all your windows. And then you're finally done with the transfer. Okay. iOctls, this is the garbage bag. Whatever you want. Okay, so this is basically for things that don't map well to read and write. In fact, you could implement read and write with iOctls. So user level iOctl in the driver, also an iOctl routine. And do we have, here's a little example. Most iOctls either retrieve status or set control information. And we've got two commands here, get status, set control. And we'll have a structure for the third argument, user level third argument, short status or short control. Here is the driver, a switch statement for iOctls. I worked with a company several years ago that had they had a card, PCI card with 4 gig of memory, and they had an operating system on the card. And the way you made calls into the operating system, they had a driver for this card. It was a 50-page long iOctl, where each case was a different system call on the card itself. It worked fine. That's the way they did it. Okay. So here, typically you're either going to copy data out to the user on an iOctl or copy data in, and some iOctls do both. They copy in data, they make some changes, they copy things out. And the copy in and copy out functions basically protect the kernel from bad addresses. All right, so the kernel doesn't panic if the user passes in garbage. And yes.
So if I'm trying to access kernel memory that's not mine, EDI.
No. There's range checking as far as the user address is concerned. It's not going to check in the kernel.
Okay, so
Okay.
if I'm copying from memory space that's not mine,
Yes, if the user's address is invalid or you try to go past the end, it'll tell you about that. If you pass it a bad kernel address, or you try to go past the end of the kernel space that you've allocated for the copy, that's your fault. Okay? No. The B copy routine does much less. Actually, the B copy routine very recently, B copy is a memory-to-memory copy in the kernel, source destination length, and very recently this routine has changed from about 7 lines of code to a couple hundred. Well, no. What they found was most B copies are very small. And they found that it was faster to actually move the bytes by just having the instructions to move the bytes, as opposed to doing repzs, repetitive looping instruction. So they actually unroll the loops, and so the routine. I remember very recently. I'm going over this, and I'm looking on my machine, and I'm saying, "Oh, here it is, 8 instructions." And somebody in the class said, "Wait a minute, this isn't 8 instructions." And we went and looked, and it's a gigantic routine now. But it's supposed to be faster.
Oh, that's partly because it's also running on super scale processing.
Yeah. So they can take advantage of interleaving, very carefully writing the assembler, but it makes the routine much more complex looking when you first bump into it. Nice to have comments. Okay, so to do ioctals, yeah, nothing new here, hopefully. Fault management, you tell the fault management framework you're fault management aware by calling DDI FM init, and you basically specify the capabilities that you are capable of. iBlock is basically your interrupt level. You can specify error reports. I think this is for PCI config space. You can register, callback handlers. In detach, you tear it down. To post an event, there's a routine FMENA generate. Actually, if you start looking in the code that's dealing with this stuff, you're going to see a bunch of stuff that is not documented. Not in the DDI. Okay? This code here is coming, I think, from the DMFE driver. And I've left stuff out because I looked at it and said, this isn't commented, it's not documented. Who the heck knows what this is? I go and look at the source. Okay, yeah, you can figure it out, but try to avoid it. So here we're posting an error report to basically to the fault management daemon, FMD. And then FMD will send it to any agents that are listening for error reports. Okay. Here we're handling an error just by posting an event. The code that actually does this in a driver, there's not a lot of code. It's actually looks fairly easy to do. All right. There's just a few places where it looks like magic because there's no documentation about what it is they're doing. Question, yes?
Are all classes of drivers fault management capable?
What Sun would like is that all drivers, yes, be e-fault capable. All right.
Are you aware of any documentation that talks about cost and time it takes to make a driver and what happens to that when you add fault management?
No. I'm not aware of any. You know, a place I would probably look is Mike Shapiro's blog, blogs.sun.com /MWS. He might be the guy to ask if he hasn't written anything about it. Okay. So here's how you set up timers, various timer-related stuff. Timeout is a way to schedule something to happen in the future. It's a one-shot timer. So here I'm scheduling foo timeout handler to run with this argument and clock ticks in the future. Clock ticks on Solaris by default are 10 milliseconds, not 1 millisecond like I think it is on Linux. And you don't need a 1 millisecond clock. It doesn't buy you anything but mostly overhead. All right. There is much finer clock granularity available to applications in Solaris. I have an application on my laptop that I can get it to generate and actually receive 60,000 signals a second. It's much better than 1 millisecond granularity. But in the kernel, it's all 10 milliseconds, clock tick. So here, not quite all, but most of it is. Here, schedule this foo timeout handler to run n ticks in the future, and then n ticks or maybe a little more in the future, the function runs. Typically, you do some kind of sanity checking here. Periodic add and periodic delete basically are using timeout, but you don't have to reschedule. In other words, it will periodically go off. Again, 10 millisecond time granularity. Delay basically sleeps. Switch out, let somebody else run. DRV usec wait, busy loops. So DRV usec wait, what happens is when the kernel is booting, it basically runs a loop to calibrate how long it takes for 1 microsecond, and then when you use DRV usec wait, it basically spins for enough time to take up the number of microseconds you've specified. While you're spinning, no one else is using the processor. You can be preempted. So there's no locks in this. All right. No. Okay, so the question is, does this change with cyclics? And the answer is no. That's the short answer, okay? The longer answer is, okay, so you're asking this question because in the kernel you really need to do something on a 20 microsecond boundary. And based on this, there's no way to really do that. You can spin 20 microseconds, but that's it. You can't say, I want this to happen 20 microseconds later. So the question now is, well, and then you mentioned cyclics. And cyclics is the way that I can get this really fine granularity at user level. So can you use this in the kernel? And the short answer is, of course you can. It's software. You can do anything you want. It's not in the DDI. Okay? So, yeah, use it, but be aware that it could change. All right? And, you know, what I'd like to do, I really wanted to do some debugging. And I think we've got about 50 minutes. So can we do some debugging? You guys have, hopefully, the people who wanted it, it's been on 2 USB sticks that have gone around. So you have these slides. If you don't have it, ask somebody with one of, there's a guy back here who has a stick. Oh, here's another guy. And otherwise, what I want to do is debugging because really that's what I like to do more than all the rest of this. Okay. Oh, that's right here. Yeah, question.
Long time back, I was reading the NT documentation in which how they handle the interrupt. That suppose you are handling a high-level interrupt and you want to do something which takes more time. So what they used to do, they have some technique to move some code to be executed
at a lower priority. Well, there's 2 ways to do it in Solaris, and this is one way. You create the task queue, and then the idea would be your high-level interrupt handler dispatches the queue and says, okay, go do something. And that guy runs typically not at interrupt level at all. Interrupt is the highest priority for scheduling purposes. So this guy runs outside of interrupt. Okay? The other way to do it is you trigger a software interrupt. Now that does run at interrupt priority, but it's not a high priority, so other interrupts can get in. And it depends on what you're trying to do as to which is better. And really, it depends also on how long you think you're going to take doing it. If you're going to take a while, the task queue way is safe. Okay? You don't want to mask out interrupts for long periods of time. Now, to do the interrupt stuff, I'm sorry, the debugging stuff. Did I press the right buttons here? What I wanted to do with this is go through a couple examples. Okay, I've got about 6 or 7 panic dumps on my machine. 2 of them I put on yesterday because I finally decided this is the way I want to do this. I'm going to risk it. In other words, I'll do it off the top of my head, and you can watch the mistakes I make, and then you can go and make the mistakes differently. And I'm going to start. I think we're going to. Which one should we do? I got to be careful here. We'll start with the really simple one. Okay. And okay, so when the system panics, it will put the dump in var crash whatever your host name is, and never mind how I came up with this host name. So it puts the dump here by default, var crash whatever your host name is. And we take a look here. Let's see, I've got 1, 2, 3, 4, 5 dumps. I must have removed one of them, and you can see going backwards in time, the May 25th one I'm finding interesting because it's a real panic. I'm sitting there watching a video and the system panicked. And it's also realistic in that I can't figure. I know what happened and why it's panicking, but I don't know how it got that way, and I can't think of a good way to come up with a way to reproduce it. So this is a little too realistic, but we'll look at that later. The one I want to look at, the simple one out of this, happens to be the last one. So there's basically, at the level of debugging, there's three tools for debugging in the kernel. There's Dtrace. Now, lots of people have heard about Dtrace. There's lots of stuff here about Dtrace. Dtrace is great, and yes, it is. And I use it a little bit for debugging in the kernel. Okay? So one of the things you can do with Dtrace, one of the things you like doing with debugging a lot of times is you want to know when a function gets called. You want to know I got called, and you want to know what the arguments are. So what you would do in the past without Dtrace is you'd have ifdefs, ifdef debug, printf, function A called, argument 1 equals blah, argument 2 equals blah, etc. Endif. And then when the function returns, you'd print out function A returns value blah, blah, blah. And you'd have ifdefs around all this. And then you'd basically get your driver working with all these ifdefs. You've got all this debugging output. And then you're finished and the driver's working. So you take out all of the printf statements. Kernel printf. Now, printf is not in the DDI, but it works fine. The DDI way to do it is CMN_ERR. Common error. CMN_ERR. But printf does work. So the problem with using printf is it can introduce timing issues. Lots of times you take them out, and then 6 months later you get a new bug and you've got to stick them back in again. And for some things, something that's happening 1,000 times a second, you're going to get swamped in printf output. You get so much output. What are you going to do with this? You got 1 million lines. Have fun. Okay? So Dtrace is really good for this kind of stuff. I use it for this. I use it kind of as a first step in debugging. Now, what happens is invariably, okay, I'm in this function and I'm returning, but what the heck's happening here in the middle? Can't Dtrace that in the kernel. At user level, you can Dtrace anywhere, but in the kernel, you can't just blindly trace anything. It either has to be entry into the function, return from the function, or a place where you've put a probe, which to some extent means you've injected some instructions. Dtrace is supposed to be zero overhead. Well, you just injected instructions. It's not zero overhead. No. So I still use printf. I use it a lot when I'm debugging, but I start with Dtrace. And sometimes I just use Dtrace. Is this function getting called? It's really good for code coverage. All right? No problem with putting custom probes. It's just you got to be careful about where you're putting them and how you're doing them. Okay? You don't want to cause performance problems. You don't want to cause timing issues. If you can avoid it. All right. Now, Dtrace has this aggregation facility so that instead of getting 1 million lines of output, you can get one line of output that says, this happened 1 million times. It's much nicer. All right. So, but I'm not here to talk about Dtrace. I'm going to do post-mortem. Go ahead.
Sun has various virtualization products. Apparently, none of them have proved useful for drivers. In theory, virtualization products can have defined certain classes of problems that you wish the hardware did.
You know, I don't do much with the virtualization stuff, so I can't comment on that. I tend to want to work as close to the metal as possible, and
I believe you. I'm just pointing out that so far you have not found virtualization is not advanced to the point that it's useful.
Well, virtualization deals with abstracting hardware virtualizing to your way so that it's problematic.
It takes you up a little bit. Yeah, but I understand what you're saying. But to be honest, I don't have enough space in my machine to do a lot with virtualization, and that is my machine. This thing that we're looking at. I don't have, the place I live is. It's small. All right. So let's take a look. So 3 basic tools: MDB, Dtrace, MDB, and KMDB. Now, MDB and KMDB are really kind of the same thing. MDB you can use for live debugging. You can use it on crash dumps. KMDB is like MDB, except you can set breakpoints and you can single step. MDB is an application. KMDB is a kernel module. Now, I'm not going to use KMDB here. I find it incredibly useful for analyzing hangs, especially a hang I can reproduce, assuming I can get into KMDB. If I can get into KMDB, I can set breakpoints and I can watch what's going on. I find it really good for that, for looking at hangs. MDB is the way you look at, is a way. There's another tool called Solaris Crash Analysis Tool, or as they ask me to say, SCAT. And it's a great tool. I don't use it because it's not what I learned. And also, SCAT does things for you, which if you're an administrator, you like. As a debugger, maybe it does a little too much for you. So I'm going to stick with MDB, and we'll run it on, so I'm running it on the 6th dump here. So the Unix file is a symbol table listing, and the VM core file is basically a memory listing. And the first thing, I'm just going to go through some standard stuff I like to do. This particular bug is going to take us about 5 minutes, because it's... Why is the command line editing and prompt not available? Because I'm using Emacs. We're not going to start that one. Yes, they do have a bias. I don't understand why, but we're going to drop it now. We'll let it. No. Stay away from it. It's a waste of energy. Okay, so I'm just getting a very brief. Here's the status. Here's what was going on. So it tells me what I was debugging, where it came from, the operating system that's running, a panic message. So this is a bad trap, basically segmentation violation, or the analogy of a segmentation violation in the kernel. It tells me it occurred in module called bad trap. What do you know? This is really kind of a injected thing due to a null pointer dereference, and the address that is causing the panic is address equal 4, which hopefully to everyone in here is obviously not a valid virtual address. Okay? So the kernel's trying to use a value at address 4, which is not valid. The address is not valid. That's right. That's right. The smallest unit of allocation is a page. So a page at address 0 would go typically from 0 to 4K or 8K. 4 is in that page. We can't allocate it. If we could allocate it, then if we could use page 0, then null would be a valid address. I have worked on a system with valid null pointers, and it's not pretty. Okay? Now, let's take a look at the console output. Okay, so command I'm running here is : message buff. And it's basically at the beginning is not interesting. Where I want to see this is if I suspect hardware issues. Then I want to look at the whole message buffer, because there may be messages in here. But generally what I'm interested in here is at the end of the output. So we got a panic. It occurred on CPU 0. It tells me the thread that was running when the panic occurred on that CPU. Gives me the panic message again, a bad trap. This will be the most common kind of panic you're going to get in a driver, especially when you're doing your when you're in development anyway. It will give me the command that was running cat. So somebody was running cat. It tells you process ID, which I find generally worthless, and the system isn't running anymore. Program counter. This is the location of the instruction where the panic occurred. So this is important. I want to go look here. This is where I'm dying. A stack pointer value, which generally I don't use, although I use it but indirectly. I'll show you in a few minutes. E-flags register, and some more hardware registers, CR0, 2, 3, and 4, which I'm not going to get into. Various other x86-based registers. So on x64, this looks different. On Spark, it looks different. And then a stack trace, which is 90% of the time, this stack trace is bogus, which is a technical term meaning ignore it, don't use it unless there's no other way. Why is it bogus? I don't know. But it's been that way for many years. This may or may not be accurate, but generally I found it is not going to be totally accurate. And besides, it went way past the problem. Die is basically where you're returning to the firmware and rebooting. All right? So there's another way to get to the stack. So this is what came on the console when it panicked. I ran in MDB this command, : message buff. Do that with VI, piece of junk. Now, we go on. So let's take a look at a stack trace. And if I just do stack trace $C, it'll give me the stack trace of the thread that panicked. So my machine has it's dual core. So I've actually got 2 CPUs as far as Solaris is concerned. This shows me just the stack trace on the CPU that died. And here you read this bottom to top. So somebody made a read system call. The read system call called fop read, file operation read, called spec read, called cdev read, called bdtrp underbar read. And we're dying 11 bytes in. Now here, this actually, for the most part, matches. I think this also says you're hex 11 bytes into this function. So these offsets here, plus 28, plus 27D, plus 4A, these are byte offsets from the beginning of the function of where the function will return to. So when bad trap read returns, it'll return to cdev read plus 28. When cdev read returns, it returns to spec read plus 27D. That's x86 and x64. On Spark, the same numbers would be where you were called from. All right. Now, we go a little bit further with this. So at this point, what would you normally do if you were debugging? We can look at the program counter. I actually might go a little bit, I might just jump ahead a little bit, but whoops. Everyone see this? So program counter on 32-bit x86 is the EIP register, and I'm retrieving the EIP register and dumping out the instruction. So here's where we're dying. Now a move is basically memory address to a register. So the memory address it's moving from is 4. It's obviously not correct. And we're dying 11 bytes, hex 11 bytes into this bad trap read routine. What would you do now? I know what I would do. Exactly. I'd go to the source. You guys with me on this? Why spin wheels? This one's easy. By the way, they're never this easy. Just in case there's any misconception. Oh, it's debugging is easy. If it's easy, they'd automate it. We wouldn't be here. Somebody would automate it. Let's take a look. Where did I put it? Let's try. No, I use cscope. I don't use ctags. And if you guys want this little driver, you want to panic your machine, it's actually instructive. I was actually thinking when I was asked to do this of having, telling people, oh, bring your laptop and we'll do this. But I realize now that we can't do this in 3 hours. So here's bad trap read. It's pretty short. And if we look at the assembler code, actually some of you should be able to look at this already and know what the problem is, but let's bring the assembler code back up. Now I'm just going to dump out the entire function. There's the assembler code for the function. So MD, if you didn't get this yet, by the way, there is no C-level debugger for the kernel. You want a C-level debugger for the kernel? Write one. Let it be a challenge, an opportunity. There was at one point, there was a debugger called KSLD, Kernel Source Level Debugger. This was in Sun, and it was there for about 6 months in 1998 or 99. And then it disappeared. The people were moved to other projects, and I saw a paper by this guy in Sun who it was like a one-page paper entitled something like "Why Source Level Debuggers Are for Losers." You want a source level debugger? No, be my guest. I maintain that at some level you're going to have to get here anyway, especially with drivers. Now, so here's the source code, and hopefully everyone sees what the bug is, yeah? Yeah, RSP null. No, there's nothing wrong with setting RSP to null. No, the problem is that I set it to null, and here I do this. What's the fix? So the dip field is 4 bytes into this structure. That's why we're getting an address of 4, and the fix is to swap these two lines. Could we be any simpler? I mean, I wanted a simple example. Here you are. Okay, so one issue you're going to have is that you're going to be told where in assembler you're dying. And an issue you're going to run into is you're going to need to figure out, based on this, where is it in the code? For this one, you don't need to. You look at the code and say, there's the problem. But you got something you got a 50-line or 100-line function, and you're dying somewhere in the middle, and you have to try to map the assembler back to the C code. This can be very difficult. The optimizer can do all kinds of things with your code. No, this is, wait a minute. I don't remember.
I thought one of the first rules of driver development is leave the optimizer off until you're reasonably sure you didn't step on yourself.
Is there anything that tells me if it's optimized? Yeah, I don't think elf dump does it. Dump S tabs at one point would tell you how it was compiled, even with the path name to the compiler. But I could look at the make file. I'm sorry? You do not strip kernel modules, period. Okay, if you want to play the game, you don't strip the kernel modules. So, but the optimizer actually should show me. Where did I put this? Oh, that's nice. Yes. Looks to me like it's on. I could just build it again to check, but I think it is probably on. And yes, I'm shooting myself in the foot by doing that, but
So sometimes it's easier to reverse compile if you don't leave the optimizer.
yes. Yes. Yeah. One other thing. If you have the source code, it's your driver, you can always add -S and rebuild. Don't change it. You can keep all the flags in place. Optimization, everything. And by the way, we don't use more than level 3 optimization in the kernel. It's -03. We don't do higher. All right. Solaris kernel does not use higher than level 3. Above level 3 can do things like it'll get rid of, well, here, let me go back to this. Okay, you'll see here at the beginning how it does this prologue, pushes the frame pointer, moves the stack pointer into the frame pointer. It builds a new stack frame. Above level 3, gets rid of this. It makes it, you can't unravel the stack, at least not easily. Yeah, well, yeah, but it does it for all functions, not just leaf functions. This actually is not a leaf routine. It calls DDI gets off state.
Oh, so that's a true procedure call. It doesn't expand into an inline.
No, but it will actually get rid of the pushes. It will basically get rid of the linkage to set up to look at your stack frame. So $C won't give you output. So we don't do it in the kernel. Makes debugging almost impossible. Also, if Dtrace doesn't see this, you can't function bound trace it either. All right. If again in the make file -S, and it'll produce a .s file. And the .s file will have the assembler code with your C code in comments. And that's even with optimization turned on. So you can actually, that's the easy way to do this. You have to map back to the assembler. I occasionally get these panics where I don't have the source code. Sometimes somebody sends me a panic from a Solaris 9 box. I go and look at this. I don't have the source code. You're forced to look at the assembler. Question, yes? Okay. Well, I'm ready to move to the next. So.
So the comment is made regarding Dtrace not being able to see the function boundaries. That would apply if your code is optimized. If it's non-driver level code that you've optimized above level 3, Dtrace can use the function.
Well, Dtrace doesn't do function-bound tracing at user level. Okay. It can trace any instruction, so it's not quite the same thing. It does function-bound tracing, but the way it does it is it looks for this push and move, and it saves the push and move and replaces the instruction with an int or a... now what it does is a lock move. And the lock move causes a trap. I'm sorry, okay, look. Oh, the PID provider, but this is user level. I'm in the kernel here. No, I didn't say that. I said the user level doesn't do function-bound tracing. You can trace functions, but it's not the same. It's not the same mechanism. At user level, it replaces whatever instruction at whatever location you want to trace. In the kernel, you have function bound tracing. You can trace entry and return, but only if it does this prolog. And on Spark, it's a save instruction. On x64, it's a push queue, move queue. All right. If they're not doing this at the beginning, you can't do function bound tracing on that function. That doesn't mean you can't come up with a way to trace it. So mutex enter. I didn't talk about synchronization at all, but mutex enter. You grab a lock, mutex exit. You release a lock. There's no function bound tracing on those because they don't do this standard prolog. It takes too much time. Mutexes are used all the time. It's very fast. We do 5 or 6 instructions to grab a mutex, assuming there's no contention. And 5 or 6 instructions, we don't want to do this push and push at the beginning and pop at the end. We just practically doubled the number of instructions that need to be executed. Okay, so you can't trace it. So what if I wanted to trace it? You'd write a wrapper function. Trace the wrapper. Okay, my mutex enter. And then inside my mutex enter, you call mutex enter. And then you trace my mutex enter, which you can do because it's a normal function and does the normal prolog and epilogue stuff. All right? What's that? Okay, let's, yeah, I think we've got this one. Just one or two other little things. Okay, so now I'm still in MDB on the dump, and I'm running, I want to see what's on the CPUs. So on the first CPU is cat, and the second CPU is running the X server. Cat, there's a bash process waiting to run on the first CPU, and on the second CPU, some kernel thread waiting to run. Sched is kind of a generic name for any kernel thread that doesn't have a user level. And what tends to be important in here is who was running. If there is an interrupt, this BSPL field will have some additional information in it. And one other thing that tends to be important here is this switch field. This is a time. And if you see T minus some very big number, it means that this thread is not, this processor is not switched to a different thread in a long time. The numbers are clock ticks. So it's T minus 30,000 means you haven't switched in 30 seconds. Or 300 seconds. All right, which is a long time. You shouldn't see big numbers. If you are, then something's wrong. All right. So this I'll look at more when I'm looking at a hang. You know, what's everybody doing? All right. So this one's not that interesting. Let's look at the more interesting bug. Yeah, well, we'll see. This one I debated. Well, let me get started because there's one step in this that may take the rest of the time. So, this one is number 4, and whoops. Okay, so here is a page fault. It's another bad trap, basically a bad address. And the address looks a little bit funny. Anyone recognize the address at all? BADDCB2A? Okay. Yeah, okay, the kernel has a pattern that it uses for uninitialized data. The pattern it uses is bad cafe. And this looks to me like kind of like bad cafe with something added to it. So bad cafe, it's picking up a pointer, I'm guessing, right away. I'm guessing it's picking up a pointer that wasn't initialized, it's adding an offset, and it's giving me this value. So it's using the pointer like it's pointing to a structure and going and trying to pick up a field in the structure, but the pointer's garbage. But right away, I'm just guessing based on that number. It tells me it happened in Gen Unix. Oh, great, problem solved. Bug's probably in Gen Unix. No. Yeah, Gen Unix does not have any bugs. Okay. All right, so again, it says it's an illegal access to a user address. On x86, 32-bit, the kernel starts... where does it start? Yeah, let's do it this way. Okay, at least on my machine right now, the on this dump, the kernel starts at CEC02000, virtual address. On x86, anything below that is a user address. The kernel is only above that. On Spark, all bets are off. This address could be it could be either user or kernel. And on x64, the kernel starts in the high order 2 terabytes of the 64-bit space. So this would definitely be a user address on x64. So it tells me it's a user address, but really, this is the panic code making a guess. It doesn't really know. Illegal access to a user address. It's a bad address. That much it got. All right. Let's take a look at the message buffer. Again, what was on the console? And for those who missed this, okay, it's : message buff. Dumps out, basically, the message buff output is not going to be all the output ever going to the console. It'll be roughly the last 8K. Okay, up to and including the time of the panic. So I go and look at this. And again, tells me the CPU 1 this time, tells me the thread that was running, tells me it was a page fault, tells me the bad address, the program counter, stack pointer, various registers. You'll notice there's at least one register in here. Here's another one with values of bad cafe. This bothers me. And again, gives me a stack trace which may or may not be reasonable. Okay so far? Now, I'd say let's take a look at the program counter. And I can either cut and paste the PC value, or if I know the name of the register, it's the EIP register. And I'll just get that one instruction. So it's dying at VN has cache data plus 6. It's doing a compare of 0 with whatever happens to be at the EAX register offset by 2C. And what's in the EAX register? Bad cafe. It's not a valid address. And 2C plus bad cafe, if I add those together, I'll get the bad address that I got. Okay, that's the address where it's dying again. I just added the two values, 2C plus the value of the register. Okay, so bad cafe. So why am I getting bad cafe? Well, if you look at this, you got an argument. What the heck is the argument being passed to VN has cache data? It's bad cafe. So I don't think the problem is in VN has cache data. I think the problem is in do DNLC reduce cache. Okay so far? I want to see how this gets called. How does VN has cache data get called? How's it? What is this thing? What is this function doing? Now, so at this point, what would you do? Well, we're going to do what I would do because we don't have a lot of time, and I've done this a little bit. So I'm going to look in the source code, and I happen to know that this code, where did my stack trace go? Well, this code is in something called the DNLC. Let's get the stack trace back up here. Here it is. So what I really wanted to look at was do DNLC reduce cache. Now, for those who don't know what the DNLC is, this is the directory name lookup cache. It is a cache of, I really want my tablet. Why isn't it working? It's a cache of parent directory vnode, file name, and vnode for the file. It's used by NFS, UFS, ZFS. So all the file systems use this. And it makes path name lookup fast. So what's path name lookup? You've got a path name, /user/bin/vim. Okay? The system has to convert that path to a vnode. So what it does is it goes and uses this DNLC to try to do the conversion as fast as possible. Are we okay? Now, let's take a look at the code where do DNLC reduce cache. That's the one I want. Let's see. Here's do DNLC reverse cache. And looks like it calls VN has cache data. So I'm just going to go where it's called. There it is. Is that the right place? Yes. Now, what this routine does, it turns out, is the DNLC, basically, if you do a find on a large system that has lots and lots of files, and you just do find slash, it'll just fill up this directory name lookup cache with all the files in your machine. So what can happen is this can get quite large, and the system has this thread that comes along and periodically kind of looks around and says, oh, we're getting a little big here, and it tries to trim it. That's the reduce cache. So it's trying to clean things up a little bit to free up some space. Okay? And you can see that when the routine gets called, VN has cache data gets called, it's being called with an argument VP. Now, VP in the kernel is, I would venture to say 100% of the time, this is a pointer to a vnode. Okay? And I think that this vnode pointer is bad cafe. Now, my next step was actually, what I thought I would do is actually look at the DNLC. Look at all the entries. Okay? That's what and this is the step that might take longer than we have time for. But we're going to try it anyway. Okay? So what I'll do is, now, rather because we don't have a lot of time and because I've done this kind of stuff before, I'm just going to tell you. The cache, the name service cache, has a hash chain. The number of entries in the chain depend on the size of the memory. On my machine, the number of entries in the hash array is 16,000, basically 16K entries. The 0T in the front of the number indicates it's decimal. By default, everything in MDB is hex. And for those of you who work in hex, you'll say that great. And for those of you who don't, maybe you should write a source level debugger. No, sorry. All right, so what we're going to do is the cache itself, I don't remember the name of, so we'll look for it. Oh, it's nope. That looks good. Okay, so it's a pointer to NC underbar hash. And the idea is that this pointer points to virtually contiguous space of 16,000 entries. Each entry is a pointer. So what I'm going to do is I'm going to take that pointer and I'm going to dump out 16,000 entries. Each one is a NC hash T. And maybe we're just going to dump one first so we can see what the structure looks like, because otherwise... Okay, so here's the first structure. There's, again, 16,000 of these in an array. And each entry in the array is a pointer to a hash list. So what this function up above, it turns out what it does is it basically walks this list and it looks for old guys and trims them out and makes the list shorter. And the idea of this is that we try to keep the list so that it's no more than 4 entries deep. So that when we're doing searches for path names, we never have to follow a chain that's more than 4 entries. System does this in a few other places for other data structures as well, where it's not using AVL trees. We don't want to use AVL trees here because we're constantly adding and removing. All right. So what we're going to do is we're going to print out the hash underbar next value for each entry to go to the next entry in the chain. So you have an array, you hash into the array to get an index, to get a slot, and then you follow a linked list starting at that slot looking for a match. That's the directory name lookup. Oh, you're asking why don't I just go to the one where I know it's bad cafe? And the thing, well, maybe that's not what you meant to ask, but... No, actually, what I'm going to do here is I'm going to look for one that's bad cafe, and the way I'm going to do this is dump them all out. Okay. The problem with this is this can take time. There's 16,000 entries, and right now, yes, that's what I'm going to do. Right now, there's AC0C total name cache entries. So this is close to 60,000 entries in the name cache. So what I'm going to do is I'm going to do the walk. And this, I'm going to just do everything in one line. Did I get, whoops, I'm missing some colons here. Uh-huh. Okay, that's the first, this is basically walking the first slot on the list. Now I'm going to walk all 16,000 slots. Okay. So it's working. It'll start giving me output or it'll die on me, but I think I got this right. The first one looks good. So it Okay, so the syntax here basically there. BI. Okay, so basically what you do with MDB is you start with an address. So my address here is not NC hash, it's what NC hash points to. And you give it a count, which is optional. Here I'm giving an a count of 16K, hex 4000. If you don't, the comma indicates the count. If you don't give it an account, it assumes 1, exactly. Then ::print is something called a D command. So MDB has a couple hundred D commands. And print is the one that I tend to use more than anything else. And with print, you can specify the type of the object that you're printing. So these 16,000 NC hash entry structures are all NC hash Ts. It's a type def. It recognizes only kernel types. It actually does recognize user types for most of the standard libraries. But, okay. And I'm only going to print in this structure, I'm only going to print this field, hash next, which is the chain to the next guy going down. So again, my tablet is just not working, but I have an array. I index into the array, and then I follow a linked list of ncache structures, which is out here. So once I've got the first entry, the next pointer, I pipe this output into another MDB command. And this MDB command follows a linked list. You tell it the type of each entry in the list and how you get to the next guy. Okay? So this follows the linked list of ncache structures that are hanging off the hash slot. And from there, I pipe it into print, and I print out ncache underbar T. And I did this last night, I remember, and I went out to dinner, and when I came back, it was still printing, so I'm only going to print out the vnode field. Okay, because that may not be done, but it may be close enough. So at this point, I'm going to look for bad kept. Whoops. Yes. I'd say 10 minutes. Oh, there it is. Okay. 10 minutes. Yeah. Here's bad cafe. There's my entry. And by the way, I've done this. There's only one place where this happens. Now, I did make a mistake because I don't know which cache entry this is. I don't know where I am. I just know I've got a VP that's in the cache that has bad cafe in it. That's where I'm got to be dying. It's the only place in the entire cache that has it. All right? So, well, I don't know if it's obvious from the code. I'm just trying to get as much information about it as I can. So what I did, since I did make a slight mistake here, I did finish, I'm going to add one little thing to this. I'm going to get, when I'm doing the print, this -a option is going to show me the address of the field. Because from that, I can get the rest of the structure for that particular guy. So there's one that occurs right at the beginning, and I haven't looked at that one at all. You can see. Whoops, I got the -a in the wrong place, sorry. I don't want the -a there, I want it right after the print. And here we may as well add that just for completeness. So what this will do is it'll show me the address of all the VP fields. And then if I can find, am I still screwing some? Oh, 0A, thanks. How many more typos can I make? There we go. So if I have the address of the field and I know what the offset of the field is from the beginning of the structure, I can dump out just that particular ncache. And what I found when I did this, by the way, is that ncache is 48 bytes large, the structure, plus the file name, which is additional space, 48 bytes altogether, but the entire thing contains bad cafe. Before it looks like regular data. After it looks like regular data. So my thought was, well, this can't happen. Because if you look at the code, they allocate the entry, and then they immediately fill it in. It shouldn't. When they allocate the entry, that's when it's going to get bad cafe. The very next thing they do is fill in the structure. The only way it would happen is if somebody else came from outside and stomped on it, or if I allocated it and then instead of continuing on, I went off somewhere else. But the code doesn't do that.
So this only happens when you're displaying certain graphics stuff, right?
No, it only happened one time. This is what's real about this. I talked with somebody last night about this, and he said exactly what I thought, which is, if I can't reproduce this, there is no way I'm going to solve this.
Yes, the most common category of bugs is
Yes. Cannot be reproduced. But yes, bug closed. If you get a reproducible case, let us know. We'll take a look at it again. Yeah. And that's exactly where I got with this. I followed it, and I looked at the code and found the structure, looked around the structure, but I want to do that still. Let's see if we've got it up here yet. Here it is, with the address. Have fun doing that with VI. And I can't resist it, you notice. Okay, so this structure, we can kill that. It's an ncache underbar T. The vnode field is 8 bytes in. So I can take the address that I have and subtract 8 bytes. And we'll do it all. Okay, here it is. And the whole thing's bad cafe. And in fact, if you look at the code where they allocate this structure, you'll notice that the char1 name, well, the name field can be variable length. So when they allocate this space, they allocate space for the structure plus the actual string length of the file name that you're putting into the cache. And it turns out that the 312 Is that what I want? Yeah. CA, bad cafe. And then I said, well, where's this address coming from? Where am I getting this address? So we'll just take it to 0. Where is this coming from? So I use : what is? And this is going to hopefully tell me something about where it's from. And what it will tell me is it's coming from kmem_alloc plus kmem_alloc 48. It's 48-byte kmem_alloc. Well, I think CA bytes is larger than 48 already. The structure just, it's not right. I think it's been stomped on. Can't reproduce it. So eventually it's going to say kmem_alloc plus 48 because I've done it. I looked at it. Well, the thing is, if it was a buffer overflow, I'd expect the stuff before it or after it to also be bad cafe or garbage, but it looks like reasonable data to me. There it is. So I take a look at it. We'll just back up a little bit.
Do you think the graphics driver is in any way involved in this, or is it just incidental?
I think it's incidental, but I don't know for certain. Somebody else last night mentioned the graphics driver. They assumed for some reason that it was NVIDIA. Don't know why, have no comments about that, but here's right before it, looks like reasonable data to me, and right after it also looks like reasonable data. It's just these 48 bytes of bad cafe. Unless I can reproduce this, I'm not going to get any further. And when I can reproduce it, then I think more about, well, how can I debug this? No. In fact, the one thing that I use, that I unfortunately still use Windows for, is what you just asked about.
Because 48 is sometimes a special number. 48
Yeah, but see, I think 48 sounds very likely for a name cache entry also. The structure, the name cache followed by path by some file name, 48 bytes sounds reasonable. I think the structure 1, 2, 3, 4. I got 5 times 4 is 20. 6 times 4, 24. So I got about 24 or so. 24 byte file name. That's a little large, but not extravagant. Yes.
So that sort of suggests that this entry is not initialized. It has pointers to it, but it doesn't. But the initialization of the line didn't occur.
No, actually, I misspoke. When you allocate from using kmalloc, the buffer that gets allocated is stamped with bad cafe before calling a constructor function. For kmalloc, there is no constructor function. It's for kmcachealloc, there's a constructor function that does any normal initialization. So bad cafe is basically an uninitialized pattern for the buffer.
Yes, but so there's two ways to end up with bad data. Something wasn't done or something extra was done.
Yes. Yeah, and it could have been either one. Yeah, I see what you're saying. Yeah, it could have been either one. As far as I'm getting with this. Okay, guys. We're done, I guess. Thanks, guys.